They say that between 1880 and 1930, more loggers in the Pacific Northwest were killed by steam donkeys than by falling trees, snapped cables from hand operations, and animal-related accidents combined. Not just more, significantly more. The steam donkey, a machine designed to solve the impossible problem of moving massive logs out of terrain where animals couldn't work, became the most lethal piece of equipment in the deadliest industry in America. It was a portable steam engine with a drum and a cable that could drag a 40-ton log up a mountain through a half-mile of forest. It revolutionized logging, made fortunes for timber companies, and opened forests that had been unreachable. And it killed with such efficiency and variety that the men who operated them were considered either the bravest or the most suicidal workers in the woods. Cables snapped and cut men in half. Boilers exploded and scattered body parts across acres. Sparks from the firebox ignited forest fires that trapped entire crews. And the companies kept building them, kept deploying them, kept hiring new operators to replace the dead ones, because the alternative was leaving billions of board feet of timber standing in places that horses and oxen simply couldn't reach. This is the story of John Dolbear's invention, the machine that saved the logging industry and slaughtered the men who ran it. How it worked, why it was necessary, and how it killed in ways both predictable and horrifying. Let's start with the problem, because you can't understand why the steam donkey was revolutionary without understanding what it replaced and why that wasn't working. In 1880, the logging industry on the Pacific Coast had a bottleneck. The forests, Douglas fir, redwood, Sitka spruce, were being cut at increasing rates. Demand from cities, railroads, and construction was insatiable. But the trees were standing in terrain that defied conventional logging methods. Steep slopes, ravines, distances from navigable water. The standard method was animal power. Bull teams or horse teams pulling logs on skid roads, greased timber pathways that reduced friction. But animal power had limits. A team of 12 oxen could pull maybe 10 tons on flat ground. On a slope, less. And the distance they could work was limited by their endurance and the need to return them to camp each night. If a log was cut 3 miles from the landing on a steep slope, it could take a week to retrieve it with a bull team, if it could be retrieved at all. Many logs were simply abandoned because the cost of retrieval exceeded the value of the timber. This was unacceptable to the companies. They had paid for cutting rights. They had invested in camps and infrastructure, and they were leaving product in the woods because they couldn't move it. The economic pressure to solve this was immense. John Dolbear was a timber operator in Humboldt County, California, running operations in the redwood forests around Eureka. He wasn't an engineer by training. He was a businessman, a mill owner, someone who understood profit and loss. And he saw the loss represented by logs left in the woods. Dolbear's insight was to apply a technology that already existed, the steam engine, to the specific problem of log transport. Steam engines were common in mills, powering saws and planers. They were used in ships and locomotives, but they were stationary or mounted on vehicles designed for smooth surfaces. What Dolbear envisioned was a portable steam engine, small enough to be moved, but powerful enough to pull loads that animal teams couldn't handle. He built the first prototype in 1881. It was crude but functional. A vertical steam boiler about 4 feet tall and 2 feet in diameter, mounted on a heavy wooden sled. Attached to the boiler was a single drum, a cylinder of iron wrapped with steel cable. The steam from the boiler drove a simple engine that turned the drum. The cable could be run out into the forest, attached to a log, and wound back in, dragging the log to the machine. The whole contraption weighed about a ton, light enough to be dragged into position by a team of horses, then anchored in place. Dolbear tested it on his own timber tracks. The results were immediate and dramatic. The donkey could pull logs that a bull team couldn't move. It could work continuously as long as there was fuel and water. And it didn't get tired, didn't get injured, didn't need rest. The productivity gains were staggering. A single steam donkey could do the work of 3 or 4 bull teams. Dolbear filed for a patent in 1881. The patent described a portable engine for hauling logs and other heavy materials, emphasizing the portability and the mechanical simplicity. The patent was granted, and Dolbear began manufacturing the machines commercially. Other companies immediately saw the potential and began building their own versions, often skirting the patent with minor design changes. By 1885, steam donkeys were operating throughout the redwood belt of California and starting to appear in the Douglas fir forests of Oregon and Washington. By 1890, they were standard equipment. A large logging operation might have a dozen or more donkeys working simultaneously. The machine worked through brutal simplicity. The firebox, fed with wood or coal, heated water in the boiler. The steam generated pressure, typically between 100 and 200 pounds per square inch. That steam was directed into a cylinder where it drove a piston. The piston was connected to a crankshaft that turned the drum. The drum was wrapped with cable, anywhere from a quarter mile to a half mile of 3/4 inch or 1 inch steel cable. The cable ran out from the drum, through the forest, to the log. A crew of choker setters would wrap a choker, a loop of cable with a slipping noose, around the log. They'd signal the donkey puncher, the operator, who would engage the drum. The cable would tighten, the drum would turn, and the log would start to move. The log didn't follow a road. It went in a straight line from wherever it was to wherever the donkey was positioned. It plowed through brush, over stumps, through ditches. If it hit an obstacle, the cable tension would increase. The donkey puncher would feel it through the controls, through the vibration in the machine. He'd add more steam to increase power, or he'd back off if the tension got too high and risked snapping the cable. A good donkey puncher could feel the difference between a log hung up on a stump and a log rolling free. He worked by sound and vibration because he couldn't see the log. It could be a quarter mile away, out of sight in the forest. The operating crew consisted of the donkey puncher, the engineer who controlled the steam and the drum, the fireman who fed the firebox and maintained boiler pressure, and the rigging crew, the choker setters and the signalmen who worked out in the woods. The donkey puncher and fireman stayed with the machine. The rigging crew was scattered through the forest, setting chokers, clearing obstacles, signaling. Communication was by whistle. A steam whistle on the donkey, operated by a pull cord that ran out to the rigging crew. 1 whistle meant stop. 2 meant go ahead slow. 3 meant go ahead fast. A long, continuous blast meant emergency, drop everything, someone's hurt or dead. The companies loved the steam donkey because the economics were undeniable. A donkey cost about $500 to build in 1885, roughly $15,000 today. It could be operated by a crew of 4 to 6 men, compared to the 12 to 20 men needed for equivalent work with animal teams. The operating cost was fuel and wages. Fuel was cheap, often scrap wood from the logging operation itself. Wages were higher for donkey crews, $3 to $4 a day for the puncher, $2 for the fireman, $2 for choker setters. But the total labor cost was lower than animal operations, and the productivity was double or triple. A steam donkey could move 20 to 30 logs a day. A bull team might move 5 or 6. The return on investment was measured in months. A donkey could pay for itself in a single season. So the companies bought them, deployed them, pushed them hard, and the donkeys started killing. The cables were the first and most persistent killer. Steel cable under tension is storing enormous energy. The physics are straightforward. A 3/4 inch steel cable has a breaking strength of around 25 tons. But the working load, the safe load, is a fraction of that, maybe 5 or 6 tons. The problem is that working conditions in the forest were never safe. The cables ran over rocks, stumps, through dirt. They abraded. They kinked when a pull went wrong and had to be straightened. Straightening a cable weakened it, creating stress points. The The cables were exposed to moisture, which caused rust. Rust weakened the individual strands, and the cables were reused day after day, week after week, until they failed. When a steel cable under tension fails, it doesn't just break, it whips. The stored energy is released instantaneously. The cable becomes a projectile, moving faster than the eye can track. A quarter-mile of cable under 5 tons of tension, when it snaps, will whip back toward the donkey or toward whatever anchor point is holding the other end. Anything in the path is severed. In 1884, a choker setter named Martin Hendricks was working a donkey operation in the redwoods near Fortuna, California. He was in the process of setting a choker around a log when the main line cable, already under tension from a previous pull, snapped 100 yards uphill. The cable whipped down the slope. Hendricks was struck across the neck and shoulders. The cable decapitated him and severed his left arm. His body was found still holding the choker he'd been setting. The official company report listed cause of death as cable failure due to worn equipment. No one was held responsible. The donkey was back in operation the next day with a replacement cable and a replacement choker setter. In 1889, a rigging crew of 3 men was working in the path of a cable under heavy load. The log being pulled, a 40-foot redwood section weighing an estimated 25 tons, had hung up on a stump. The donkey puncher increased power to free it. The cable tension spiked. The cable had a kinked section from a previous jam. The kink was a weak point. The cable snapped at the kink. The section between the donkey and the break point, about 200 feet of cable, whipped across the work area. All 3 men were hit. Thomas McCarty was cut across the waist. The cable severed his spine. He died instantly. James Killian was struck across the legs, both femurs broken, femoral arteries severed. He bled out in minutes. Peter Swenson was hit in the chest. The impact broke ribs and drove fragments into his lungs and heart. He died before help arrived. The company response was to issue a directive that men should not work in the direct line of the cable. The directive was unenforceable because the nature of the work required men to be near the cable to set chokers and clear jams. The deaths continued. In 1891, a cable under extreme tension during a pull on a steep slope snapped and whipped uphill. The cable traveled over 300 yards, still carrying enough energy to be lethal. It struck a bunkhouse where off-shift workers were sleeping. The cable tore through the wooden wall, struck 2 men in their bunks, and exited through the opposite wall. Both men died, one from a crushed skull, the other from a severed torso. The bunkhouse was moved further from the landing area. The donkey operations continued. The reason cables kept failing was economic. A new cable was expensive, $50 to $100, depending on length and diameter. A cable could be used until it broke. Companies didn't replace cables on a schedule. They replaced them when they failed. This meant that every cable in use was operating at or near its failure point. The workers knew this. The donkey punchers knew it. The choker setters knew it. They worked around cables that hummed with tension, that vibrated, that showed visible fraying. And they accepted it because refusing to work meant being fired and replaced by someone who would. But if cables were the most common killer, boilers were the most spectacular. A steam boiler is a pressure vessel. Water is heated until it becomes steam. Steam occupies more volume than water. In a sealed vessel, this creates pressure. That pressure is useful. It drives engines. But it's also dangerous. If the pressure exceeds the vessel's capacity, the vessel fails. The failure is explosive. The boilers on steam donkeys were built to a standard that was rudimentary by any measure. Riveted steel or iron plates, cylindrical or vertical design, with a firebox at the base and a steam outlet at the top. They were equipped with pressure gauges and safety valves designed to release steam if pressure got too high. But the gauges were often inaccurate, and the safety valves could stick, malfunction, or be deliberately disabled by operators who wanted more power. The primary cause of boiler explosions was low water level. The boiler had to maintain a water level above the crown sheet, the top of the firebox. If the water level dropped below the crown sheet, the metal was exposed directly to the fire. With no water to absorb the heat, the metal would overheat, weaken, and fail. The failure was catastrophic. When a boiler exploded, the release of superheated steam was instantaneous. Steam at 200 psi and 300 degrees Fahrenheit expands violently when the pressure is released. The explosion generates a shock wave. The boiler itself, weighing hundreds of pounds, can be propelled like a missile, and the shrapnel, fragments of the boiler casing, rivets, fittings, becomes high-velocity projectiles. In 1895, a steam donkey operating near Grays Harbor, Washington, suffered a boiler explosion. The firemen had allowed the water level to drop while focusing on maintaining steam pressure for a difficult pull. The crown sheet overheated and ruptured. The explosion was heard 3 miles away. The boiler casing split apart. Fragments were found up to 200 yards from the site. The fireman was killed instantly. His body found 30 feet from where the donkey had been, scalded and crushed. The donkey puncher, who had been standing to the side of the boiler, was struck by shrapnel. He died from his injuries 2 hours later. 3 choker setters working 100 yards away were caught by the steam release. All 3 suffered severe burns. 1 died that night. The other 2 died within a week from infections. The donkey itself was destroyed. The company's response was to send a replacement donkey and a new crew. Operations resumed within 5 days. In 1902, a donkey operating in Mendocino County, California, exploded with such force that witnesses reported the boiler was thrown 50 feet into the air before crashing down 100 yards from its original position. The cause was determined to be a stuck safety valve, combined with an inexperienced fireman who didn't recognize the danger signs. The explosion killed the fireman and the donkey puncher instantly. It also ignited a fire in the surrounding slash and timber debris. The fire spread rapidly, trapping part of the rigging crew. 2 men died in the fire, burned when they couldn't outrun the flames through the dense undergrowth. The total death toll from that single incident was 4, with 2 others seriously burned. The investigation, such as it was, concluded that the fireman was at fault for incompetence. No changes were made to equipment or training standards. Boiler explosions continued throughout the steam donkey era. Some years saw a dozen or more across the Pacific Northwest. Each one killed an average of 2 to 4 men, and each one resulted in the same response: replace the equipment, hire new men, continue operations. The fires were a different category of death. Steam donkeys were inherently fire hazards. The firebox was an open flame. The smokestack emitted sparks. The operation took place in forests filled with combustible material: sawdust, bark, slash, the debris left from logging operations. During dry seasons, the forests were tinderboxes, and the steam donkeys were constantly throwing sparks into them. In 1894, a steam donkey operating near Coos Bay, Oregon, sparked a fire that grew into a conflagration. The fire started small, a spark from the smokestack landing in dry sawdust near the donkey. The firemen saw it and tried to extinguish it, but the wind picked up and the fire spread into the slash. Within minutes, it was out of control. The rigging crew, spread out over a quarter-mile of forest, had no warning. The fire moved faster than a man could run, driven by wind, feeding on the dry undergrowth. 12 men were in the path of the fire. 3 made it to a cleared area and survived. 9 were trapped. Some tried to outrun the fire and were overtaken. Others tried to shelter behind logs or in ditches. None of those strategies worked. The bodies were recovered over the next 2 days. Most were burned beyond recognition. Identification was made by location and personal effects. The company's liability was disputed. The fire was ruled an act of God, an unforeseeable consequence of weather conditions. No compensation was paid to the families beyond the standard practice of wages owed up to the date of death. Forest fires sparked by steam donkeys became common enough that insurance companies began refusing to cover timber operations during the dry season unless specific precautions were taken. Some companies complied, installing spark arresters on smokestacks, clearing larger areas around donkeys, keeping water barrels on site. Others ignored the recommendations and continued to operate, gambling that they could finish the season before a fire started. Sometimes they won the gamble, sometimes they didn't. The men who operated the steam donkeys were a specific type. They had to be. The job required technical knowledge, steam engines weren't simple, combined with a willingness to accept constant danger. The donkey puncher controlled the machine. He managed the steam pressure, engaged and disengaged the drum clutch, judged the tension on the cable, and made split-second decisions about when to pull and when to stop. A good donkey puncher was worth his wages. He could maximize productivity, avoid cable breaks, and keep the crew alive. A bad donkey puncher killed people. The training was minimal. If you had experience with steam engines, from ships, locomotives, or mills, you could transition to donkey work. If you didn't have experience, you learned on the job, working as a fireman first, watching the puncher, absorbing the knowledge. Some companies offered a few days of supervised operation. Most didn't. You were hired, shown the controls, and expected to figure it out. The pay was good, $4 to $6 a day for a donkey puncher, at a time when general labor paid $1 to $2. The fireman made $2 to $3. It was enough money to save, to send home, to drink away in town when the season ended. But the turnover was high. Men quit after a season or two, burned out by the stress and the close calls. Men were fired for incompetence or drinking, and men died, regularly enough that there was always a need for new operators. The culture among donkey crews was fatalistic. They joked about death. They drank heavily. They developed superstitions, refusing to work certain donkeys that had bad reputations, believing that some machines were cursed. And they were proud. Operating a steam donkey was skilled work. It carried status in the camps. A good donkey puncher could find work anywhere. The stories they told in the bunkhouses were about close calls, about cables that almost snapped, about boilers that almost exploded, about the time they saved the crew by shutting down at exactly the right moment. And they told stories about the men who didn't make it. Tommy, who got caught by a cable in '06. Big Jim, who was on the donkey when it blew in '09. The Swede, whose name no one remembered, who burned in the fire at Coos Bay. The stories were a way of processing the trauma, of acknowledging the danger, and of asserting that they were still alive, still working, still beating the odds. Over time, the steam donkey evolved. The early models, like Dolbear's original, were small, single-drum machines. By the early 1900s, manufacturers were building larger, more powerful models. Double-drum donkeys, with separate drums for the main line and the haulback line, allowed more complex rigging. Triple-drum models added a third line for loading or for running skylines in high-lead logging. The boilers got bigger, generating more steam, more power. The drums got wider, holding more cable, allowing longer reaches. And the danger scaled with the power. Bigger boilers exploded with more force. Heavier cables under higher tension whipped with more energy. Larger operations, with multiple donkeys working simultaneously, multiplied the opportunities for disaster. Manufacturers began to implement safety improvements, slowly and reluctantly. Better pressure gauges, more reliable safety valves, stronger cable. But the improvements were incremental and often ignored. A company could buy a modern donkey with safety features, or they could buy a cheaper used model and push it until it failed. Most chose the latter. Regulatory pressure began to build in the early 1900s. State governments in Washington, Oregon, and California started to investigate industrial accidents. Labor unions, still weak in the logging industry, pushed for safety standards. Insurance companies, facing massive payouts, demanded changes. But enforcement was minimal. Logging camps were remote. Inspectors were few. Companies could ignore regulations with little risk of consequences. It wasn't until the 1920s that serious regulation began to take hold, driven by a combination of public outcry, union pressure, and the financial strain of insurance costs. By then, the steam donkey was already being replaced. Gasoline and diesel engines offered similar power without the boiler explosion risk. Tractors and trucks provided alternatives for log transport in accessible terrain. Railroads expanded into timber country, reducing the need for long-distance cable skidding. The steam donkey didn't disappear overnight. They were used in remote operations through the 1930s and 40s. Some were still working in the 1950s in places where the terrain made other methods impractical. But their dominance was over. The peak era, 1880 to 1920, was also the deadliest period in logging history. Estimating the total death toll from steam donkeys is difficult because records are incomplete. Company ledgers recorded deaths that happened on shift and that the company acknowledged. They didn't record deaths from injuries sustained on the job, but that occurred later. They didn't record deaths that were covered up or misattributed to other causes. But historians, working from surviving records, newspaper accounts, and coroner's reports, estimate that steam donkey operations killed between 1,500 and 2,000 men in the Pacific Northwest alone between 1880 and 1930. That's an average of 30 to 40 deaths per year, every year, for 50 years. Cable failures accounted for roughly half. Boiler explosions and related steam injuries accounted for about a quarter. Fires, both donkey-sparked and incidental, accounted for another 15%. The remainder were a mix of crushing injuries, falls, and secondary accidents related to donkey operations. To put that in perspective, the total number of loggers killed by falling trees, widowmakers, and barber chairs during the same period was lower. Not by much, but lower. The steam donkey, the machine designed to make logging safer by removing men from direct contact with falling trees, ended up killing more men than the trees themselves. What remains today of the steam donkey era is scattered and rusted. In the forests of the Pacific Northwest, if you know where to look, you can still find them. Abandoned steam donkeys, left in place when operations shut down. The metal has rusted, the wood components have rotted away, but the boilers, the drums, the frames, they're still there. Massive iron artifacts, slowly being consumed by the forest. Some are in museums. The Dolbear steam donkey is on display at the Clark Historical Museum in Eureka, California, a restored example of the original design. Other museums in logging country have examples, restored or rusted, displayed with placards explaining their function and their history. The placards rarely mention the body count. The physical scars of steam donkey operations are visible if you know what to look for. Cable scars on trees, deep grooves worn into the bark and wood where cables ran under tension, blast sites where boilers exploded, still identifiable by the scatter pattern of metal fragments and the disturbed soil. Fire scars, sections of forest that burned in steam donkey fires and regrew as different species or different age stands. The human legacy is harder to trace. The men who died have graves, some marked, many not. The small cemeteries in logging towns have sections filled with young men, dead in their 20s and 30s, buried between 1880 and 1920. The stones often don't list cause of death, just names and dates. But the clustering of dates, multiple burials in the same week or month, hints at disasters. The regulations that came out of the steam donkey era are still in effect, in evolved form. Boiler inspection standards, cable certification requirements, worker safety protocols. Much of modern industrial safety law can be traced back to the disasters of the late 19th and early 20th centuries. Laws written in response to specific explosions, specific cable failures, specific fires. The problem was that the laws came late. They came after hundreds of men had already died. And they came because insurance companies demanded them, not because companies or governments valued worker lives. The economic calculation was always clear. Men were cheaper than downtime. A dead donkey puncher could be replaced in a day. A destroyed donkey took weeks to replace and cost hundreds of dollars. So the companies invested in equipment durability, not worker safety. John Dolbear, the inventor, lived to see his machines spread across the industry. He also lived to see the death toll mount. There's no record of his personal response to the casualties. He didn't write about it. He didn't speak publicly about it. He continued to manufacture and sell steam donkeys, and he died in 1913, a wealthy man. His legacy is complicated. He solved a real problem. His invention made large-scale logging economically viable in terrain that had been inaccessible. The timber that came out of the forests because of steam donkeys built cities, built railroads, built the infrastructure of the West. But the cost was measured in bodies. 1,500 to 2,000 men killed by a machine that was revolutionary and lethal in equal measure. So here's to the donkey punchers, the men who stood next to boilers that could explode and managed drums wrapped with cables that could snap. Here's to the firemen who fed the fireboxes and watched the pressure gauges and hoped the safety valve would work. Here's to the choker setters who worked in the path of cables under tension that could cut them in half without warning. Here's to the rigging crews who ran when the whistle blew the emergency signal and who didn't always run fast enough. Here's to Martin Hendricks and Thomas McCarty and James Killian and Peter Swenson and the 2 men killed in their bunks and the 6 men killed at Gray's Harbor and the 4 men killed at Mendocino and the 9 men killed in the Coos Bay fire and the hundreds of others whose names are lost but whose deaths are documented in company ledgers and newspaper archives and cemetery records. They operated the machine that killed more loggers than falling trees. They did it for wages that were good, but not good enough. They did it because the alternative was poverty or starvation, or going back to a life that offered even less. And they did it knowing the risks, because the risks were obvious, visible, discussed in every bunkhouse and around every campfire. The steam donkey is gone from active use now, replaced by machines that are faster, safer, more efficient. But the legacy remains. In the rusted hulks scattered through the forests, in the regulations written in blood, in the graves of young men who died operating a machine that their employers knew was deadly and deployed anyway, because the timber had to come out, and the profit had to be made, and the cost in human lives was, in the cold calculus of industrial capitalism, acceptable. The machine that saved the logging industry slaughtered the workers. That's not metaphor, that's documented fact. And we owe it to the men who died to remember that the boards and beams and structures built with the timber those machines moved were bought with more than money. They were bought with lives. The steam donkey killed more loggers than falling trees, and it did it for 50 years, in broad daylight, with full knowledge of the companies and the government and the public. That's the legacy. Not just the innovation, but the cost. Not just what was built, but who paid for it. The forests are quiet now where the donkeys once screamed and hissed. The cables are gone, the boilers are cold. But the ground remembers. And as long as we tell the story, we remember too.